Hello everyone, I'm Alan Pereira. Today we'll be present Filling the Gap, the work of a technical artist. It is a pleasure to be here today, and I hope I can share some valuable knowledge with you. Before I get started, I would like to share a little about me. So I'm a technical artist at gamedevelopment Montreal. Have been working as a generalist technical artist for about 6 years on games for different platforms, as mobile, PC, and in consoles. I currently work at Disney during Light Valley, and there is also some other projects I have worked during my career. Here is a summary of the topics that I'll be covering in this session. I'll begin with a brief introduction about what is a technical artist, and then I will start to talk about the most common demands in emerging gaming industries I observe in my career as a generalist. We'll cover what is a technical artist, asset integration, asset pipeline, rendering pipeline, and optimization. So what is a technical artist? For everyone that might have searched about this for the first time, have probably stumbled with the definition that a technical artist is a role that fills a gap between art and engineering, or something very similar to this. But this statement alone is pretty vague. What is this gap? And, or even better, why does this gap exist in the first place? This has to do with the increasing complexity of game development. As games are always trying to innovate and bring new technologies, the processes of creating the art up to those requirements and also their integration became something way more technical than what artists were used to. And the need to know about art fundamentals and some digital content creation tools made it not suitable for a programmer to do this as well. So this created the need of having a role that knows about technical stuff like graphic programming, rendering pipeline, game engine, and also know its ways in art creation like 3D softwares, color theory, animation principles, composition, etc. And this role is the technical artist. Starting with our common demands, asset integration is by far the most common demand here. Almost all technical artists I knew started working with it, including me. To give context, on smaller studios, you usually don't have a set of tools that allow the artists doing the integrations easily, needing someone to be that bridge that will make possible to get the assets from the DCC tools. It is Blender, Maya, 3ds Max, those are the DCC tools, inside to the game engine like Unity, Unreal, Godot, or a custom game engine, right? On this demand, you'll be working almost the entire time within the game engine. So it is really helpful for a general technical artist because you have less software to worry about as you are learning other stuff related to the game development production like Scrum, Jira, documentation, verse control, and etc. Okay, so what's needed to be integrated in this demand? The first thing you have here is 3D models. It could be a character, 3D model, or environment prop. For those integrations, you need to have some base knowledge in 3D. So having experience in any 3D software is something that will really help you here. Other related knowledge that I need are material setup. Most of the time it revolves around knowing the PBR workflow. PBR stands for physically based rendering. Knowing stuff like what is a albedo map, normal map, metallic map, occlusion map, and how to set up them into the game engine. And talk about maps, we have texture compressions. You have to understand that textures really have assets, and using the right compressions will really save the amount of memory usage your game takes. And the final item here is rigging. You don't need to know everything about rigging at this stage, at this demand, but know at least how it works, and also retardant will really help you. Retardant is what allows to reuse animation on one character and to another. For 2D, you have to worry about texture compressions, because inside the game engine, your sprites will be treated as texture as well. You need to know about Sprite Atlas or Sprite Sheet, depending on your game engine. Sprite Atlas is this collection of sprites, and this allows you to reduce the number of draw calls that your CPU will issue to the GPU. Another thing that could also result in some performance optimizations are sprite meshes. Sprite meshes, like for example, every sprite will be drawn as a quad in your scene, and having sprite mesh, it kind of have like the outline. It will be a 2D mesh here that will follow the outline of your sprite, and that will kind of reduce transparent pixels areas and thus having less overdraw. Moving forward, we have UI integrations. For UI integration, we also need to know about sensor compression, sprite atlas, but we also need to know about UI systems. UI systems are the systems that will allow you build, construct the UI inside the game engine, okay? So it could be Unity's Canvas or the Unreal's UMG. Here will be create panels, buttons, manage front assets, create a list of items that will be scrolled, anchoring stuff in the right place, making it able to adapt in different resolutions, and more. Another asset that we have here are VFX. For VFX, you have to know how particle systems works on your game engine of choice. It might be handy to have some experience on 3D modeling and UV mapping here as well, as it will allow you to do effects in more creative ways. For shaders, I do believe that having at least a base knowledge will help you here, be it to create a small vertex animation or the salvo effect, for example. This base knowledge involves knowing your inputs, like what is the mesh data, it is vertices, vertex colors, UV, normals. Also know about the simple vertex programs, simple fragment shader programs. And as a final item here, I would include knowing at least a little about object space, word space, and clip space. Note that if your studio has a specialized VFX artist, you'll be working more as a supportive role for this kind of demand, like create an Uber shader for this VFX artist to work with, okay? The next demand that we have here is asset pipeline. An asset pipeline is a series of steps for the asset production. In this demand, you'll be responsible for defining and maintaining a pipeline that suits the needs of your project, but it still allows the artist to focus more on the art creation. It's kind of a step forward from the asset integration that we discussed previously, because at this point you'll be acting more as a facilitator to get stuff into the game instead of integrate everything by yourself. Here are some things that needs to be defined within the pipeline. The softwares that should be used, naming conventions, file format conventions, triangle budget, tester size, tester channels structure, and materials library. Here there is a very simple pipeline, like you first model, you open the UV, you baking the high poly information into the low poly, you texturize it, make the rigging, and then render it inside the game engine. So it's a very simple one, just to illustrate here. Have a more complex one here from the Envar. It is a art pipeline from Envar Studio. Here we have the concept, the sculpting of the high poly, rough topology to create the low poly here, and making the UV mapping. Have baking and texturing paint here on Substance and 3D coat. Have here create the rigging, the skinning, and it is. After that, it would be game ready, right? We could integrate inside the game engine and also be animated by the animation artist and etc. But the idea here is that you'll be shaping the pipeline. And to shape your pipeline, you first need to understand the steps that you need for your project. For example, not all mobile games require creating a sculpted high poly, so you could remove them. It would remove like the sculpting, the topology, and also the bake of tester, because all those are some resulting steps of the sculpture of having the high poly. So if you don't have the high poly, you have less steps to create a 3D model for a mobile game and would deliver 3D models way faster. Another thing that you should check is if all those software are really needed. Like here we have Substance Painter and 3D Coat for the baking testing paint. 3D Coat is an awesome software for hand painting, but if my game only features PBR stuff, we might be able to do everything on Substance Painter. It would be one less software to worry about. And the less amount of software, less licenses you have to pay, less friction work export and import stuff you have, and also less APIs in your code to maintain if you are doing tools. A final thing to consider is how many assets needs to be made, because it's not doable to have a complete pipeline that take months to deliver one character model if you have to deliver like 100 of them in 6 months. You have to adapt that pipeline, be it by removing some step or automate them. Sorry. And by automation, we have here tools. In this demand, in the demand of creating tools, we need to identify pain points, the development, pain points that pipeline that we shaped. And then we'll be creating tools that will solve those issues by streamlining their workflow for the artists. Note that pipeline tools are different from game systems. So game system would have like vegetation, terrain, etc. For pipeline tools, we try to solve problems external to the game engine. Usually it involves knowing Python, specific scripting languages like Mel or Max scripting, PowerShell, and DCC tools APIs. For pipeline tools, the rule of thumb is that if it is a repetitive action where you do the same thing over and over, it should be automated. Some pipeline tools example are custom exporters. It can be to export something from one DCC to another, like from Maya to Substance, or it could be to export to the game engine. It generally saves a lot of time setting exporting parameters that are always the same. We also have rigging tools. It could be some auto rig tools similar to 3ds Max Sketch or Blank's Rigify, but with your game's needs in mind. We also have asset processor. It could be described as a more advanced set of tools where you have well-defined rules and behaviors for your assets, how your assets are made, how your assets should look in a lot of occasions. And having those well-defined rules will allow you to automate most part of its creations. So if you are interested in asset processor, I recommend watching this talk from Embark Studio. A final tip here is that it's also important to document your tools. A good documentation will not just help the artist to learn how to use your tools, but it will also help you in the case of improvement or bug fix is needed. Aside the assets, another part of the game development that technical artists are responsible of is define how things will gonna be drawn to the screen. And that comes by knowing about rendering pipeline. Rendering pipeline is a sequence of steps that render the graphical elements into the screen. It can be 2D, 2D, or even the UI. It will pass through some rendering steps before being drawn to the screen. Render pipeline can vary depending on the implementation, but here are some common steps. So given an input mesh, we first send the vertices of the element we want to render. Those vertices are transformed through a vertex shader. Generally here, you will just adjust the vertex to be in the right position, the word space. We then generate the triangles and pass to the rasterization step. The rasterization step is where the vector elements are going to be transformed into pixels. And with the vector elements as pixels, we have the data to run the pixel shader, also known as a fragment shader. Here is where the pixels are going to be shaded. In other words, receive the colors. It will sample the texture and also calculate the lighting. Also, we have the final color of the pixel. We can do some operations like blending for transparency or sensor for discarding a given pixels. With that, we send the final color of those pixels to the frame buffer that will be later displayed on the screen. Moving forward, we have rendering pipeline implementations. Well, like I said before, the rendering pipeline can have different steps depending on the implementation. And the technical artist's job here is to define what implementation better suits the game you are developing. And also what technologies are you going to support, like post-processing effects, ray tracing, dynamic resolution, and etc. For the implementations, we have the following render pipeline that are most common. We have forward renderer, where the light is calculated per object and additional lights require additional passes. We have the forward rendering, where the lighting is calculated all together on a separate pass. It uses more frame buffers, but it also has issues with transparent materials and does not support MSA and Chalise technique. We also have forward plus render, which is similar to forward render but use clusters that allow more additional lights. On the features, have a bunch of things to consider. First off are culling techniques. Those allow to eliminate geometry that are not visible on the screen, so we do not waste resource trying to render things that are not visible. The most common are frustum culling, occlusion culling, and backface culling. Another thing we have here is LOD, level of detail, which reduce the complexity of objects that is far from the camera. So by reducing complexity, I mean it allows you to use a simpler mesh, but it also allows you to use a simple shader or material, so it will take less resource to render that object that is far from the camera and does not need to have all of the details visible because it will be too small on the screen. Have anti-aliasing techniques like MSA, FXA, and TAA. Then we also allow to find the ones that better fits your needs. Have post-processing, that exists a lot of different post-processing effects, but the most common are tone mapping, exposure, color adjustment, bloom, motion blur, screen space ambient occlusion, screen space reflections, ray tracing. By ray tracing, we also have ray tracing reflection, ray tracing shadows, ray tracing global illuminations, and etc. Following here, we have dynamic resolution. So some examples are FXR and DLSS from NVIDIA, FXR from AMD. Other features that we could have are compute shaders, like here from Ghost of Tsushima, it's a compute shader that rendered the grass. Have foliage, which pretty similar, outline effects, volumetric fog, pixelization, and more. Now, the last domain I want to discuss today is all about optimization. Ultimately, optimization is what we do to keep our game running in the desired frame per second. Frame per second is our majority metric to know if your game has a good performance or not. But I say we have a frame budget measuring milliseconds, and this budget is defined by our target frame rate. For example, in mobile games, generally we are speaking of 30 FPS. So I have to generate 30 frames in 1 second. And for us to have our frame budget number here, we could just divide 1 second or 1000 milliseconds by 30, and we get our frame budget milliseconds. In the case, it is 33 milliseconds to work with. So everything that our game does, be it on the CPU or in the GPU, has to work within those 33 milliseconds. Moving to PC and console, we'll have 60 FPS. And if you do the calculate here, we would have 16 milliseconds. So if I want to have my game running 60 FPS, I have to make everything work within those 16 milliseconds. Another standard is 90 FPS for VR. This has to do with issues like disorientation and nausea if the game is presenting a slower frame rate. But in general, with our frame budget, we now have a metric to know if each one of my graphical feature is doing fine or not. And before moving on more advanced stuff regarding optimization, it's cool to understand our resource, what we have to work within those milliseconds, the frame budget that we calculate. Have the CPU and the GPU, and also the memory. In general, the idea will be to balance the workload between the CPU and the GPU and maintain the memory usage by allocating only what is needed and deallocating what is not in use anymore. So here are some common scenarios where things start to go wrong. The first one is CPU bound. We have CPU bound where our CPU is our bottleneck, which means it's taking longer to prepare a new frame to send it for the GPU to render it. So just to give some context, the CPU is always one step ahead from the GPU. It starts this way. The CPU calculates everything from one frame and gives this new frames for the GPU to render. So the CPU is always one step ahead. And if the CPU is taking longer to calculate, the GPU here, we have to wait. So we have here the CPU thread, and below we have the GPU thread here. So if the CPU is taking longer, the GPU thread will kind of wait, and that means that our CPU here needs to be optimized. Something in the CPU needs to be optimized in order for us to reach our 16 millisecond, for example. And the vice versa scenario is GPU bound, where our CPU is doing the job, but the GPU is taking longer to produce a frame. So every time that the CPU will send a new frame for the GPU, it has to wait this GPU to complete the previous frame before sending a new frame for this GPU. In this scenario, our GPU is the bottleneck, and it is what needs to be optimized. Sorry. Last common scenario here is out of memory. The out of memory scenario is not related to the FPS at all, because it doesn't drop the FPS, but it actually crashes the game. This occurs when your game tries to use more memory to what is available for it. It's most common on mobile platforms and handheld consoles like the Nintendo Switch, where you have less memory to use. Okay, but those are the scenarios, the common scenarios of when things goes wrong. But how do I get this data? How do I know that my CPU is take like 21 milliseconds? How do I tell that my GPU is waiting, or the vice versa? How can I get this data? This is where profiling comes in. To understand what is your bottleneck, what is taking more resource than expected, and find how can we optimize it, we need to profile first. And on profile, we have the usage of tools that will sample your game and present valuable information, like how many milliseconds a feature is taking, how many memory usage your assets are taking, and the frame data, and more stuff. So all that information will make it easier to understand what and where you should optimize. Here is a list of common profiling tools. We have Unity Profiler, Unreal Profiler, Android Studio Profiler, Xcode Instrument, Firefox Profiler. Those, for the Firefox here is for WebGL applications. We also have frame analysis. This is more recommended for technical artists, because most of the time you will be trying to understand how your frame is being constructed to see if it's taking the desired steps or desired passes on your shader, on your rendering pipeline. And the frame analysis tool is what allows that. So we have here RenderDoc, Unity Frame Debugger, Microsoft Pix, NVIDIA Inside Graphics, AMD Radeon GPU Developer Tool Suite. Just before moving on, I just want to state here the optimization model, which is always profile first. There is no issue in profiling. Just have in mind that profiling really takes time. So aside optimization tasks where you will have to profile, if you will just want to validate if your game is running fine periodically, you could do that when a new feature is introduced or before a new release. If you have a remote machine, you can even try to automate it to do some more general profiling daily. Okay, well, most of what I said was focused on a generalist, technical artist, mainly focused on emerging game industry, right? But on a AAA studios, the amount of work is too much for just one person to be able to contribute in every demand. Thus, the need of specialized roles. Here are some specializations to look after. Have tools and pipeline, have procedural, have rigging, materials, and shaders. On tools and pipeline, you'll be most doing asset integration and the asset pipeline demands. In procedural, you might be taking most computer shaders or game tool systems. At rigging, it's pretty focusing on rigging tools. And here, and they also create the controllers for the animators, right? And on material shaders, it's pretty that, material and shaders. You'll be creating shaders, you'll be giving maintenance to the material library of your game, and that's it. If you want to know more about those specializations, I really recommend take a look at this talk, A Day in Life of the Tech Artist from Ginomon at YouTube, okay? Well, that's it, guys. At the end of the day, technical art is all about handling pretty frames and empowering the artists, either by easing the development process or adding some handful tools for them to bring their creativity to life. I really hope that you learned something new today that could make your valuable time here worthy. And thanks again for the IGDA team for the opportunity.